At the end of the last lecture, we started discussing about a technique to calculate the correlation involving n terms. For example, in one dimension, if you want to evaluate the integral Zn is equal to integral dx e raised to I lambda f of x raised to n, then you have to consider z of a is equal to integral dx e raised to I lambda f of x plus I x a. Okay, if I take the derivative of z of a, then each derivative will bring down a factor of x, right? If I do one derivative, then one x will come down, right? Because differential of e raised to I x a with respect to a will be e raised to I x a I x, right? So if I do one derivative with respect to a, then it will bring down 1x. So if I do n derivatives with respect to a, then I'll get x raised to n. So one derivative can bring down a factor of x. Therefore, if I do it n times, then I get a factor of x raised to n. So Zn is equal to 1 by I raised to n, nth derivative of z of a with respect to a. And then finally we have to put a equal to 0. So if I put a equal to 0 here, then I will get this back. So first I have to take n derivatives, and finally if I put a equal to 0, then I can go back to my integrand. So in one dimension, if I want to evaluate this integral, right? If I want to evaluate this integral, then I have to consider z of a, right, which is given by this expression, and I have to take n derivative and finally put a equal to 0 so that I can integrate. I can get rid of e raised to I x a and I can get the integration done. Okay. So if you know z of a, taking derivative is much easier than doing the integral. So rather than doing this integral, if I know z of a, then it is easy to take the differentiation or the derivatives. Okay. So z of a can be expanded in power series. So how do I do that? Summation n equal to 0 to infinity I raised to n by n factorial Zn a raised to n. Okay. So this Za we call it as the generating function. Generating function. Okay. So here Zn is the coefficient of a raised to n. Okay. So the same idea can be used to generalize the endpoint function. Okay. In vacuum time ordering of x of t1 up to tn. But here we have a functional integral. So the generating function becomes generating functional. So that is the difference here. So when you come to the endpoint function, then the generating function becomes generating functional. And the analog of a here will be j, where j is a function. Okay, j is a function. So we introduce a path integral z of j of t, which is equal to integral dxt exponential I s x of t plus, so instead of Ixa, here it will be I integral dt, right? I integral dt prime j of t x of t. So this is something like e raised to Ixa that we have seen earlier. Okay. So this will be the generating functional. So this will be the generating functional. And the range is minus infinity to plus infinity with boundary value 0. So if you have more than one dimension, then you have to sum over all the Ixa for multiple x. Similarly, here we write integral j of t. Okay. If we take a functional derivative with respect to j of t, then we can bring down a factor of x, right? Similar to the case of generating function where we brought down the x by taking the derivative with respect to a. Here if I take the derivative with respect to j, then I can bring down a factor of x of t. So let's define j of t prime and derivative of j of t. Let this ratio be the delta function. Okay. Then z of j by j of t will be equal to, okay, so I am taking differential with respect to j. So what does this mean? This means the differential of z of j with respect to j. So one I will come down, integral dx, then x also will come down. If I am taking one derivative, then one x will come down. Then e raised to is as it is plus integral j of t x of t, right? So one x of t came down due to the differentiation with respect to j of t. And now if I put j equal to 0, okay, after this differentiation, if I put j equal to 0, then here you can see you will get back the integrate what you want here, the same thing. If you want n points, then you have to do n time differentiation. This is just for 1 point function. Okay, so if I put j equal to 0 in the expression for z, then I'll get integral dxt e raised to is. So if j is equal to 0 for z of j equal to 0, so let me call z of j equal to 0 as z0. This will be equal to integral dxt e raised to is. Okay, plus 0. So 0 we don't have to consider because e raised to 0 is 1. Okay. Now, by comparing with gn, so in the last class we have defined gn as integral dx of t x e raised to is x of t divided by integral dx of t e raised to is x of t. Okay, so we can find the 1 point function by dividing these two, right? So the 1 point function will be equal to So we have taken the derivative here, this divided by the z0. If I divide these two, then it will be of the form, on the right hand side you can see integral dx, then x of t e raised to is is there, then here divided by dx of t e raised to is. So if I divide these two, then I will get the 1-point function. So I am writing 1 by I, 1 by z0, because I am dividing by z0, z of j derivative with respect to t, and I have to put j of t equal to 0 as well, right? So this is the 1-point function. If I want to get the n-point function, then gn will be 1 by, I have to do this n times, so 1 by I raised to n, 1 by z0. How many derivatives I have to take? N times derivative of z of j with respect to j of t1 and with respect to j of t2 up to with respect to j of tn, and then put j equal to 0. That will be the n-point function. Okay, so we can also write z of j by z0 is equal to time ordering of e raised to I integral dt j of t x of t. Okay, this is because z of j of t we have already defined here. See, this is the generating functional z of j of t. Here if I separate these two, so instead of this plus here, if I remove this plus and if I put e raised to I integral dt j of t x of t, then see, this is the path integral, and if you insert some operator in the path integral, then you will get, yesterday we have defined this, if you have the path integral and if you give some operator here, then you will get the n-point function, right? For that particular operator, for this particular operator, you will get the correlation function. Similarly, I can write z of j as correlation of this function, because it is some path integral multiplied by e raised to integral of I dt, which is time ordering of that particular operator, right? Yes. And you already have divided by z0, so the coefficient will cancel, because z0 will also have c by root of determinant form, and z of j will also have that path integral, which will get cancelled off, and finally you will get only the correlation. Fine. Okay, so we can treat this piece to be our correlation function, and here x can be anything. So what is the importance of this time ordering of the exponential, right? What is the importance of the time ordering of this exponential? The power series expansion of x of t in the exponential is a polynomial, and each object of the polynomial can be time ordered. So this can be 1 plus I integral dt j of t, right? Time ordering of x of t plus etc. So the power series expansion of x of t in the exponential is a polynomial, and each object of the polynomial can be time ordered. Therefore, I can write this is equal to summation n is equal to 0 to infinity, right? So, in general, I can write these terms as I raised to n. So, when n equal to 0, I raised to 0 is 1. So, this is the first term. Okay, when n equal to 1, I get the second term. So, second term I raised to n by n factorial. So, when n is equal to 1, I get I raised to 1 by 1. Then integral dt up to dtn. Okay. So, if n is equal to 0, then only 1 will remain. If n is equal to 1, then here there will only be dt. So, for each term I have to generalize. So, dtn, then I have to write j of t. So, for nth term, j of t up to t1 up to j of tn. Then for this I have to generalize. I can write gn t0 up to tn. So, in general I can write the generating functional divided by the generating functional at j equal to 0 in this form. So, this is the general form. Okay. So, now we will consider a particular example. For example, a harmonic oscillator is always a best example to study any situation. The action for a harmonic oscillator can be written as minus infinity to plus infinity integral dt half x dot square minus half omega naught square x square. Okay, this is the action. Now the Hamiltonian is given by p square by 2m plus half omega naught square x square. Now here I am going to do the same trick that I have done yesterday, so that the Hamiltonian can be changed to 1 minus I epsilon. Okay. So h is equal to, then what will happen to the Hamiltonian? It will be p square by 2m. There will be 1 minus I epsilon plus half omega square x square will be there as it is, multiplied by 1 minus I epsilon. Now what will be the Lagrangian if I incorporate the epsilon? Then the Lagrangian will become half x dot square 1 minus I epsilon minus half omega naught square x square 1 minus I epsilon. Okay. Now here again I am going to use the trick. Yesterday we have done, if there is x dot square, it means x dot x dot. What is x dot? Time derivative of x. Okay. Now if I flip these two, then I'll get x and a minus will be there, right? So this will be x, the differential square x, then there will be a minus. Okay, so I am going to write it here. So instead of half x dot square, I can write minus half 1x outside, so that dt square I can write. Similarly from here I can take out, so minus is outside, so plus omega naught square, right? And here I have to multiply inside and then take the common outside, so I'll get minus I epsilon, sorry, plus I epsilon dt square. Similarly here also I have to multiply inside and then take minus I epsilon omega naught square, and there will be an x outside. So here there is x sandwiched by this object, and then there is x. So in between these two x, you have a sandwiched term in the bracket. Okay, plus the total derivatives. So here you can see omega naught square dt square, there is a epsilon dependence, right? There is an epsilon dependence, and when we apply the boundary condition, this total derivatives will vanish. Okay, and finally you will be left with the Lagrangian is equal to minus half x, in the bracket you have partial t square plus omega naught square. Okay, and here in these two terms with epsilon dependence, you can see if one derivative will give you I omega, then two derivatives, second derivative will give you I omega, which is minus omega square. So this dt square or partial derivative with respect to t square is actually will give you minus omega square, right? And here also you have I epsilon in the second term, that is the last term, you have I epsilon omega naught square. Okay, and epsilon is very small, so whatever you multiply it with, you will again get I epsilon. Okay, so here you can just write I epsilon, and this x will be here as it is. Okay, so total derivative is also vanished. So this is the final Lagrangian that you have. Okay, so here you get dt square is omega square. So I epsilon partial derivative square will be I epsilon omega square, right? And omega square is a positive number. So and epsilon is infinitesimal. Okay, so partial derivative square is negative definite operator. Negative definite in the sense, first derivative will give you I omega, second derivative will give you minus omega square. So it's not positive definite, it is negative definite operator. Okay, so negative, some negative number times epsilon you will get, and therefore I can just write minus I epsilon. Once I have modified the Hamiltonian and the Lagrangian, now the action S of x of t is equal to minus half integral dt x plus omega naught square minus I epsilon x, right? Now I have to insert delta function. So now I will insert the delta function here. So this integral will become minus half integral dt. So when I insert the delta function, I have dt prime, then x as it is, delta t minus t prime, then t square omega square minus I epsilon x, right? So this is the action. Now this delta function multiplied by this bracket, I can define it as k of t prime. So it is a matrix multiplied by this term, partial derivative square plus omega naught square minus I epsilon is equal to, I am going to define this as k t prime. Let this be equation number 1. Okay, I am going to define the product of the delta function and the with the partial t square plus omega naught square minus I epsilon as k of t prime. Then I can write the action as minus half integral dt prime x of t k of t prime, then x of t prime. Okay. So the action has a matrix structure. The action has a matrix structure. So in shorthand notation, I can always write this as minus half x k x prime. Okay. So this is the shorthand notation. So if I write something like this, then it means there is an integration like this. Okay, so x k x prime. So x k x of t prime, and there is a integration with respect to dt and dt prime. So once I know the action, now I can calculate z naught for this case. So z naught for this case will be integral dx exponential of minus I by 2. In shorthand notation, I can just write x k x prime. Okay, so it's e raised to is, and what is s? S is minus half x k x prime. And we know that already we have seen this is a Gaussian integral. This will be c by root of determinant k. If you have something like this, then the answer is c by root of determinant k. We have seen in the previous class. So the generating function z of j will be integral dx exponential of, you have e raised to minus I by 2 x k x prime plus, so generating function means plus I j x. So I'm just writing I j x, but there is an integral, okay, e raised to I j of t x of t, but in shorthand notation I'm just writing e raised to I j x. But you have to remember that j and x are metrics. Okay, so e raised to I j x in this is e raised to I integral of j of t x of t. So we have infinite dimensional version of z naught, right? So z of j is the infinite dimensional version of z naught, right? So this is integral dx1 up to dxn e raised to minus I by 2 xi aij xj plus, if I take I outside, then ji xi. So the standard integral to solve this kind of an integration will be 2 pi n by 2 by root of determinant a. A means here aij, which is nothing but k. But in general expression, I am just writing aij. So it will be determinant of this matrix aij e raised to I by 2 ji aij inverse, right? Aij inverse, then jj. This will be the solution in n dimension. So this is for one dimension, and then you have infinite dimensional version of z naught, which is given by z of j, and this will be the solution. I can write z of j, right? So this term will be constant by root of determinant k, because a here is k. We have taken k as the matrix. So determinant k, then exponential of I by 2, then j k inverse j. So this is shorthand notation. There is an integral always there. Okay, in shorthand notation I am just writing j k inverse j. Okay, so in the function language I can write this as c by root of determinant k exponential I by 2 integral dt prime j of t k inverse of t prime j of t prime. Okay, so this is the generating functional. So we have defined k here. Already we have defined k. What is k? Equation number 1. If you see here, this is k. But we have not defined k inverse. Okay, so k I have, but I don't have k inverse. So I have to define k inverse. How do I get k inverse? Integral dt k multiplied by k inverse must give you the delta function. Okay, so a matrix which is multiplied by its inverse will give you identity matrix. Okay, so same rule applies here. K multiplied by k inverse must be the delta function. Okay, so in this way I can define k inverse. So this will be equation number 2. So equation number 1 was defining k, equation number 2 defining k inverse. Okay, so in matrix form kmn, k inverse nk will be delta mk. It's as simple as that. Okay, so you have z of j and I also have z naught. Now what is the next step? I have to take the ratio of z of j z naught. If I see carefully, z of j has a c by root of determinant k and z naught is also having c by root of determinant k. So if I take the ratio, this constant will get cancelled and what is remaining? This exponential term will be remaining, right? So this ratio will give you exponential I by 2. In shorthand notation I can write j k inverse j. From here the 1 point function of x in vacuum will be 0. Because to get 1 point function we have to take first derivative with respect to j. So that will bring down one factor of j. Finally, when you set j equal to 0, 1 point function automatically goes to 0. Okay. So if you want to find the 1 point function, for example, see this actually is consistent with the results of harmonic oscillator. In harmonic oscillator you have learned that the expectation value of x will be 0 for harmonic oscillator. So have you ever thought why it is like this? Because it is something like a 1 point function. Okay, so the expectation value of x is a 1 point function. Why? Because expectation value is something like this, right? You take with respect to the vacuum. So it is a 1 point function because you have only one x. If you are doing a 1 point function, then I have to take the derivative. How many derivative I have to take? I have to take one derivative. If I take one derivative with respect to j, then it will bring down 1x. And finally I have to put j equal to 0. So when j equal to 0, this will be 0. Right? So if I take derivative with respect to j, it will bring down 1j. For example, here you can see it is e raised to exponential of I by 2 j k inverse j. So if I take derivative with respect to j, for example this j, then k inverse j will come down, right? So exponential of I by 2 j k inverse j. If I am taking the derivative with respect to j, then I will get e raised to I by 2 j k inverse j, then I by 2 k inverse j will come here. And then when I finally put j equal to 0, here there is a j present, and therefore this will go to 0. Okay, so the 1 point function of x in vacuum will always be 0, because to get 1 point function we have to take one derivative with respect to j, and that will bring down one factor of j, and finally when you set j equal to 0, the 1 point function automatically goes to 0. Okay, and therefore now let's consider 2 point function. Now let's consider the 2 point function given by the Feynman function. So g f t t prime is equal to g2, which is the 2 point function. So in 2 point function I have to take 2 times derivative, right? So I'll write 1 by z naught 1 by I square, then 2 times derivative of z of j by with respect to j of t, and the second derivative with respect to t prime at j is equal to 0. So what is z of j? Z of j was c by root of determinant k, right? E raised to, in shorthand notation I can write j k inverse j, right? And this is a constant which I can take outside, but we know that z naught is also equal to c by root of determinant k. So this z naught will get cancelled with the c by root of determinant k which is present in the z of j. Okay, and here I square is minus 1. So I can write gf t prime, the Feynman function, is the 2 point function which is equal to I square is minus 1, then derivative with respect to j. Now there are two derivatives here, right? There are two derivatives. So this is one derivative, and one derivation I am just writing it here as it is. Okay, so derivative of z of j. Z of j is e raised to I by 2 j k inverse j. So the derivative will be e raised to I by 2 j k inverse j itself, right? And the derivative of j k inverse j with respect to j. So there are two j's. So first I will do with respect to the first j, then I will get I by 2 k inverse j, plus now I have to do with the second j, then I will get I by 2 j k inverse, right? So this is the first derivative. Now one more derivative is remaining. So here I will write this is equal to minus derivative with respect to j e raised to I by 2 j k inverse j. Now I by 2 plus I by 2 will be I k inverse j. Now I have to take one more derivative. So when I take one more derivative, now derivative of, first I will do the derivative of the exponential. Derivative of exponential will be e raised to I by 2 j k inverse j itself, right? And the derivative of j k inverse j with respect to j will again give you this one, which is I k inverse j. Okay, then I have to multiply with this second term I k inverse j, plus now exponential as it is, and I have to take the derivative of the second term. So what is second term? I k inverse j. So derivative of second term with respect to j will be I k inverse itself, right? Now at this derivative is at j equal to 0. So when I substitute j equal to 0, the first term will vanish because there is a j in the numerator. this is equal to, so there is a minus here, and at j equal to 0, the first term will be 0 and the second term will be e raised to 0 I k inverse. So this will be minus I k inverse. So gf of t prime is equal to minus I k inverse. So k inverse, from this expression I can write k inverse t prime is equal to I gf t prime, right? Because this minus I, when it comes to this side, it will be plus I. So k inverse t prime is equal to I gf t prime. So let this be equation number 3. So therefore k inverse t prime is the Feynman propagator in harmonic oscillator, right? So if k inverse is Feynman propagator, then I have to go and visit equation number 1 and 2 where I have defined k. What is k, right? So I have defined equation number, equation number 2 is defining k inverse. So k multiplied by k inverse is equal to the Dirac delta. If I go to equation number 1, then I have the definition for k. What was k? This particular bracket multiplied by the Dirac delta of t minus t prime. So that was the definition of k of t. Now combining equation 1, 2 and 3, okay, so 1, 2 and 3, okay, so these three equations, combining 1, 2 and 3, I can write the bracket term, okay, that is k inverse is equal to the delta function. So this is equation number 4, okay. So from equation number 1 and equation number 2, we find that k inverse must follow this equation number 4. So if we substitute equation 3, that is k inverse is equal to I gf in equation number 4, right, then we get the exact expression for the Feynman propagator, okay. So I'll do that. So before I substitute k inverse, let's see what is this epsilon here, okay. So also this epsilon in this equation number 4 is actually the epsilon that we used in the epsilon prescription. If you remember, when we discussed about the Feynman propagators, we discussed about singularities and how to remove the singularities, and there we discussed epsilon prescription technique to overcome the singularities. So the epsilon in the equation number 4 is the epsilon that we used in the epsilon prescription of the Feynman propagator, and it can be recovered through the same procedure. So here in this expression, I epsilon came when I substituted h as h 1 minus I epsilon. So this same epsilon prescription in the Feynman propagator can be recovered through this procedure. Okay, so we can see that these formulations are consistent with each other. This procedure and the epsilon prescription are consistent with each other. Therefore, in momentum space for t is equal to t prime, okay, I can write t prime is equal to I gf of t prime. So if I substitute K inverse of 0, okay, then here it will be delta of 0, which is 1. So that is how you get K inverse is equal to 1 by minus omega square plus omega naught square minus I epsilon. Now when I substitute it here, I get GF of 0. Okay, so here K inverse is 1 by minus omega square plus omega naught square minus I epsilon, which is equal to I GF of 0. So what will be the Feynman function for t equal to t prime? This will be, so this I, when I take here, it will be minus I by minus omega square plus omega naught square minus I epsilon, right? So minus I by, I can take a minus outside here, then omega square minus omega naught square plus I epsilon. So now I can cancel the negative. So GF is equal to I by omega square minus omega naught square plus I epsilon. So from 1 point and 2 point function, we can conclude that for any n point function in general, okay, for any n point function in general, odd n gives Gn is equal to 0, that we have seen, right? For example, 1 point function will give you 0, okay, because there will always be a j left in the numerator, right? And when you put j equal to 0, Gn will go to 0. So for all odd n, it will give Gn is equal to 0. And for even n, right, even n, Gn will be something like this, time ordering of t1 up to tn, right? So here the sum of all possible contraction between x and t will be present. So by contraction, what do we mean here is that x of ti, x of tj, this pairing. So you will pair with two operators, and this is the Feynman function ti, tj. So just pair all of them, and each pair is a contraction and gives a Feynman function. So this was first proved by Wick, and this is called as the Wick's theorem. Okay, for even n, the endpoint function Gn will be the summation of all possible contraction between the various operators. Okay, so each pair will be a Feynman function, and just pair all of them, and each pair is a contraction and gives the Feynman function, right? But now we know that it is just a trivial consequence of path integrals, which is quadratic in J. So in for example, in 4-point function, if you have 4-point function, which means n is equal to 4, so n is an even number, then I have 4 points, 1, 2, 3, 4, right? So this is equal to the summation of different possible pairs, right? So what are the pairs? If I have 1, 2, 3, 4, I can pair 1, 2 and 3, 4. Otherwise I can pair 1, 3 and 2, 4. Otherwise I can pair 1, 4 and 2, 3, right? So this is equivalent to the Feynman function t1, t2, t3, t4, this one, plus GF T1 T3 T2 T4. It is the second one. And third one will be GF T1 T4 T2 T3. Okay. So with this background in quantum mechanics, you can find the analog in quantum field theory. So for today we will stop here, and in the next class we will see the time ordered functions in quantum field theory. So all this time we were talking about X, right? So these are all operators in quantum mechanics. Next we will see the time ordered functions in quantum field theory.